the invitation. And today I will give a talk by giving an overview on materials for hydrogen storage from theoretical point of view, to shed light of the underlying mechanisms of hydrogen storage, and to present some strategies for improving hydrogen. Please.
Next slide.
Next page, please.
Who's having the presentation? Next. Okay.
Yeah. Okay. As you know, the renewable energy sources are the alternative energy sources to the fossil fuels, since these later are depleting at fast rate, and they are the main cause of the pollution of our Earth. Please, next. Next. Okay, thank you. But the problem is that the renewable energies present some limitations, namely they are intermittent and fluctuating, so they can't be used permanently, and especially for transportation. So there is a critical need for secondary sources as a carrier of energy, and among the secondary sources, hydrogen is considered as a potential alternative because it is abundant on Earth and renewable, is non-polluting because it has zero carbon emission. Since it is used with the proton exchange membrane fuel cell, and by combustion it produces just water, and it has a high energy density as illustrated in this figure. The energy density of hydrogen is 3 times of the diesel. The next, please. The next slide. Okay, but the hydrogen energy suffers from some limitations, namely its production, its storage, and its distribution. And the most disadvantage of the hydrogen is its low volumetric density. For example, to produce one need 1 liter of hydrogen to produce the energy obtained by 0.27 liter of gas. Then the storage system must have for efficient use of hydrogen storage, the storage system must have a high gravimetric and volumetric densities. The gravimetric density represents the quantity of hydrogen that a given mass of the host can generate, and the volumetric density is the quantity of hydrogen gas that host volume can contain. Moreover, the storage system must have low absorption temperature and heat transfer, and of course good reversibility for multiple uses, and fast reaction kinetics, and must at low cost. Please. Next slide, please. There are different technologies for hydrogen storage, namely the compression. The hydrogen is stored in cylinders. Such technology uses a high pressure, and the hydrogen may be stored by liquefaction in cryogenic tanks by using very low temperature. These two technologies are not safe, and consequently they are not they can be not used for transportation. And the most potential technology that can be used for transportation is the absorption into solid state compounds. In such technology, there are two ways to store the hydrogen. It may be stored by as atoms by chemisorption, or it may be stored as a molecule. It's a physisorption. There are different systems where the hydrogen may be stored as atoms. For example, we have the hydride. For example, the metallic hydride and intermetallic hydride. The hydrogen is absorbed in the interstitial sheets, while in the ionic hydride and covalent hydride, the hydrogen bonds with the chemical element of the host, depending on the electronegativity by ionic chemical banding or covalent banding. The complex hydride they present the highest gravimetric capacities, but their problem is that is the fact that for their decomposition they need one need more than a reaction. In the physisorption, the hydrogen is absorbed in porous materials like carbon-based materials or carbon nanotubes, metal organic frameworks, or covalent organic frameworks, and 2D materials like graphene or phosphorine. Please, next slide. For efficient use of hydrogen storage, the US Department of Energy has defined some criteria for onboard hydrogen storage. The storage system must have a very high gravimetric capacity, about 5.5 weight percent, and must have a very high volumetric capacity, about 14 gram per liter. And for its for the durability and operability of the system, the decomposition temperature must be in between -14 degrees Celsius and 85 degrees Celsius, and the storage system must present 1500 cycles, and must for charging and discharging time, the system must have a short time for charging and discharging. So the charging rate and charging rate must be in between 3 and 5 minutes. Next slide, please. In order to study theoretically the hydrogen storage properties, we use the density functional theory. In such theory, the Schrödinger equations at stationary state may be solved in a simple way. Here, as you know, in the stationary Schrödinger equation, here is the Hamiltonian of the system. Psi is the many-body wave function, and A is the energy of the system. And here the different terms, the kinetic terms and the interaction potential terms. The density functional theory is based on two theorems, namely the Hohenberg-Kohn theorems. Such theorems state that for a system of interacting particles in an external potential, the external potential can be determined uniquely with the ground state density, and the energy the total energy can be written as a functional in terms of the density. And the ground state of the system is obtained by the global minimum of this functional energy, and such minimum is obtained by applying the variational principle of quantum mechanics as illustrated in this equation. E0 is the ground state energy that corresponds to ground state density. In order to solve the Schrödinger equation, Kohn and Cham suggest that the total energy of a system of interacting particles in an external potential is equivalent to an energy of a system of non-interacting particles with an effective potential. And they rewrite the functional energy by adding an additional terms called the exchange correlation energy. Such exchange correlation energy is the difference between the kinetic and the Colombian interaction terms for the system of interacting particles in an external potential and the system of non-interacting particles. Next slide, please. The density of the system is defined as follows. It is the sum of the squared wave functions. Such wave functions are solutions of the Kohn-Cham equation, which is a Schrödinger-like equation with three different potential terms: the external potential, the Hohenberg exponential, and the exchange correlation potential. The Hohenberg potential represents the potential of interaction between electrons. The problem is that the exchange correlation potential cannot be given explicitly, so there are two different approximations where the exchange correlation potential may be represented, namely the local density approximation, LDA, and the generalized gradient approximation, GGA. In the local density approximation, the local exchange correlation is considered as the local exchange correlation energy of a uniform gas of electrons with a uniform density. But the problem is that the density fluctuates locally. So the generalized gradient approximation takes into account of such fluctuation by writing the exchange correlation energy as a functional of the density and gradient of the density. The explicit form exchange correlation, the form of the exchange correlation potential in the LDA approximation is given by the Perdue-Wang representation, while in the GGA approximation, the representation of the explicit form of the exchange correlation terms is given by the Perdue-Burke-Enzerhof representation called PBE representation. Please, next slide. Lack of time, I will present just two different systems with two different strategies for improving the hydrogen properties. The first system is the magnesium hydride. It is considered as a potential candidate for hydrogen storage, since he has high gravimetric capacity and high volumetric capacity. But its problem is its slow hydrogen absorption, desorption kinetics, and high dissociation temperature. Experimentally, it was shown that a ball milling with a transition metal accelerates the kinetics and reduces the decomposition temperature. Next slide, please. Next slide. Okay. The magnesium hydride crystallizes in ritual structures where the magnesium atoms are located in the corner of the structure and in the center. The 4 hydrogen atoms, the positions of the 4 hydrogen atoms are given as follow, where x equal 0.34. All the results I will present are obtained from the density functional theory calculations based on full potential local orbital basis scheme to solve the Concham equations. And the exchange correlation energy is done within GGA with the PBE representation of exchange correlation potential. The next slide, please. First of all, one has to look for the minimum of the energy to determine the cell parameters. As we can see from this figure, the minimum of the total energy of the magnesium hydride is obtained for this cell parameters values. Such values were obtained theoretically are in agreement with the experimental ones. And the height formation of the equation of the formation of the magnesium hydride is determined by the total energy of the magnesium hydride, from which we subtract the total energy of magnesium and the total energy of hydrogen. The obtained value of the formation enthalpy is very high, and it is very high than the required values for onboard hydrogen storage. Such high values of formation energy indicate that the system is highly stable. Please, the next slide. Such high stability can be illustrated in the phonon density of states, since all the peaks of the density are located in the positive region of frequencies, except a small region where small peaks are located. And the composition temperature is obtained from the Gibbs potential, that vanishes at the composition temperature. So this temperature is obtained as a ratio of the formation enthalpy and the variation of the entropy of the system. Such entropy variation of the system is equal to the variation, or to the entropy variation of hydrogen, since the variation of the entropy variation of the host is negligible. So we obtain the decomposition temperature that is a very high temperature compared to the room temperature. From this table, we have drawn all the thermodynamical quantities of interest, the cell parameters, and the formation enthalpy, desorption temperature. And as we can see that the gravimetric and volumetric capacities are high, and they are higher than the desired values that are defined by the Department of Energy. Please, next slide, please. To explain such high stability of the magnesium hydride, we study the density of state of the system. So in the total density of state, we can see that the magnesium hydride is a semiconductor with a gap energy of 3.74 electron volts. And from the partial dose of density, we can see that there is a strong hybridization between the s orbital of hydrogen and the p orbitals of magnesium. So in order to reduce the stability of the magnesium hydride, one have to reduce such strong hybridization. Next slide, please. Next slide, please. Okay. To reduce such strong stability, we proceed by substituting the Mg, the magnesium atoms, by metallic atoms like aluminium, titan, vanadium, iron, or nickel. In this supercell, we present doped magnesium hydride with one element, one metallic element. And for such supercell, it corresponds to a concentration of 6.25%. Please, another slide, please. Following, okay, thank you. All the thermodynamical quantities of interest are calculated and are drawn in those tables. In the first table, we can see that for the doped systems, the gravimetric and volumetric capacities remain high. They keep their values and they don't decrease significantly. But the formation enthalpy that is given from the reaction, this reaction, presents a significant decrease as it is shown in this table. So such decrease of the formation enthalpy implies a decrease of the decomposition temperature. Please, next slide. Please. Okay. To understand such reduction of this stability, the strong stability, we study the density of state of the doped magnesium hydride. As we can see from the total density of state, the doped magnesium hydride is still semiconductor. And from the partial density of states, we can see that there is an hybridization between the s orbitals of hydrogen and the p orbitals of aluminum and the p orbitals of magnesium. So the strong hybridization that existed in the pure magnesium hydride now is shared between the aluminum, for example, between the metallic element and the magnesium. Next slide, please. In this slide, I present the variation of the height of formation and desorption temperature and gravimetric capacity as a function of the concentration of dopant element. We can see that the height formation is an increasing function of the concentration, while the desorption temperature and the gravimetric capacity are decreasing functions. From such results, we deduce that the nickel is the most appropriate dopant element for doped magnesium hydride to be used for onboard hydrogen storage for a concentration of 7.1%. We obtain formation enthalpy that is equals to 140 kilojoule per mole hydrogen and desorption temperature of 300 degree Kelvin and the gravimetric capacity of 6.12 weight%. Such values are meets the required values advised by the Department of Energy. Please, next slide. In order to study the diffusion of hydrogen in the magnesium hydride, we use the kinetic Monte Carlo. Such methods allow us to manage time of diffusion, and the time between two hops of hydrogen is is distributed according to an exponential distribution with a mean of 1 over gamma total. The gamma total is the sum of all Hoppian frequencies, and such frequencies may be given within the harmonic transition state theory, and they are given by the following formula, where delta EA is the activation energy, it is a barrier energy, and T is the temperature, and K beta is the Boltzmann constant, and nu 0 I is frequential prefactor. In the diffusion of hydrogen in magnesium hydride, there are different processes, and the energy barrier, this activation energy, must be provided to the adsorption of hydrogen as molecule at the surface, and after that to the dissociation of hydrogen molecules, and to the diffusion of the hydrogen atom between two interstitial seats or leaving the host. Please, next slide. Each process is chosen with a probability pi, and the extracted process must fulfill this inequality where U is a random number, and the time is updated from T to T plus delta T. Please, next slide. In order to study the diffusion of hydrogen, we start from an empty supercell of magnesium. Here we present a supercell of linear size of 3, and we fill by the hydrogen. The amount of gas of the gas heating unit area at the surface is given by this formula. Such equation is obtained from the kinetic theory of gases, where P is the pressure applied to the hydrogen. Please, the next slide. Different pathways the hydrogen can do, and they are represented in this figure. We can see that in the plane of the structure, the hydrogen has 7 different pathways, while in the interparallel planes there are 4 pathways. And from the study of kinetic Monte Carlo, we mentioned that the hydrogen prefers to move in the plane rather in between interparallel planes. To calculate the different activation energies, we study the variation of the energy as function of migration path, and the activation energy is given by the difference between the energy of the first of the initial position of hydrogen and the maximum of the curve. Please, next slide. To study the kinetic of the magnesium hydride, we study the variation of the gravimetric capacity of the system as a function of time, and the gravimetric capacity is given by this formula, where X is the ratio of the hydrogen. As we can see from the kinetic curve, as we can see that at first time steps, the kinetic is very fast, since the activation energies are very low. But when the number of hydrogen reaches a substantial value, the activation energies become higher, and then the kinetic becomes slower. I mentioned that for dehydrogenation of the system, we cannot completely empty the system from hydrogen that prefers to move into the system rather than leave the system. Please, next slide, please. Okay. When the magnesium hydride is doped by metallic elements, we can see that the doped magnesium hydride present activation energies less than the pure magnesium hydride. So there is a significant decrease of the barrier energies in the doped magnesium hydride. The dissociation energy of the molecule at the surface presents a significant decrease. So this implies that the system present a fast kinetic than in the pure magnesium hydride. Please, next slide, please. Okay, as we can see in the charging kinetic figure and the discharging kinetic figures, the kinetic for doped system is faster than the kinetic of the pure magnesium hydride, and the fastest kinetic is obtained within the nickel element. Okay, next slide, please. After presenting the magnesium hydride as a massive system, now I will present a two-dimensional systems, and among the two-dimensional systems that are potential for hydrogen storage, we find the 2D black phosphorene. Unlike the graphene, the black phosphorene, the structure of the black phosphorene is packed. And we can see for a monolayer of phosphorene that along a B direction, there is an armchair structure, while along E direction, we have a zigzag structure. All the structural parameters are given in this table. Here, in this case, there are the angles that are defined in these figures. And we can see that the calculated values by the FT, by the density functional theory, agree with the values obtained experimentally. The next slide, please. The different adsorbent seats are represented in this figure, and then we have the hollow seat and the top seat, top of phosphorus atom, and the bridge seat, the bridge between two phosphorus atoms. And the hydrogen molecule can be adsorbed on different orientations, namely horizontal or vertical or slopy orientation Okay, next slide, please. The bending energy is calculated for minimum distance as the total energy of the system, from which we subtract the energy of substrate and the energy of hydrogen. As we see from this table, that the obtained results show that the slopy orientation is the most stable orientation for all adsorbent seats, because we have the lower values of the adsorption energies. And the most stable configuration is the hollow configuration with slopy orientations, since we have the lowest bending energy. But unfortunately, such bending energy doesn't meet the required value of storage, which is located in this interval. Here in this figure, I presented the variation of the absorption energy as function of the distance to look for the minimum of the bending energy for different configurations. In the first figure, there is sloping orientation, a sloping orientation in two different adsorbent seat, bridge seat and top seat, while here in this figure, it is the hollow seat with the different orientations. And as we can see that the minimum of the energy is always obtained with sloping orientation. The next slide, please. In order to improve the bending energy and to improve the hydrogen properties of the phosphorin, we proceed by creating defects in phosphorin and decorate the system by lithium atoms. Different topological defects can be created. The defects that are created are the single vacancy defect and double vacancy defect and Stonewall's defect. I recall that Stonewall's defect is obtained by rotating by 90 degrees the PP band, the phosphorus band, with regard to the middle of the banding. Please, next slide. The formation energy of defect is obtained from this formula, where the capital N is the number of phosphorus atoms and little n is the number of removed atoms. E defect is the energy of defect, and E pristine is the energy of the pristine phosphorin. N equal 1 for single vacancy defect and Stonewall's defect, while n equal 2 for the double vacancy defect. As we can see from these tables, the formation energy defect for all defects are very low compared to the defective the formation energy in the defective graphene. Please, next slide. So for the decoration of the system, we place the lithium atoms in the defect, and the hydrogen molecule is adsorbed on the lithium atom. From the DFT calculations, we obtain the following results of the bending energies, and we can see from this table that for non-decorating system, the bending energies are very low and they don't meet the appropriate values of bending energy, while when the system is decorated by Le atoms, the bending energies show a significant increase. I recall that the bending energy is calculated from the total energy of the whole system, from which we subtract the energy of lithium, the decorated defective phosphorin, and the energy of hydrogen molecules. The next slide, please. In order to understand the underlying mechanisms of the adsorption of hydrogen, we study the charge density of the system by calculating the differential charge densities. Such differential charge densities are obtained from the total charge density of the system, from which we subtract the charge density of the lithium decorated defective phosphorin and the charge density of the hydrogen molecules. As In the representation of such differential charge densities, the lithium atoms are represented by the red color, and the dark blue colors represent the hydrogen molecules, while the yellow colors presents the accumulation of charge, while the light blue color represents the depletion of charge. As we can see, that there is two regions of accumulations and depletion of charge on either side of the hydrogen molecules. So there is a strong polarization of the hydrogen molecules. Such strong polarization leads to or implies that the hydrogen bonds with the lithium atom following a weak electrostatic dipolar mechanism without any hybridization or covalent bonding. Please, next slide. The last slide. Okay. In order to calculate the gravimetric capacity of the system, we proceed by decorating the defective phosphorane in two sites. And we calculate the gravimetric capacity from this formula, where P is the number of hydrogen molecules, and Q and QR are respectively the number of phosphorus atoms and lithium atoms. The obtained value of the gravimetric capacity is equal to 5.3 weight%. It is high values that meet the required values defined by the Department of Energy, but it is less than the gravimetric capacity obtained within the decorated defective graphene. But it is worthwhile to mention that the formation energy of defect in graphene, in phosphorane, is the formation energies of defect in phosphorane are less than the formation energies in defective graphene. So in the phosphorane, we need less energy to create defect. In this figure is represented the variation of the bonding energy and the gravimetric density of the number of hydrogen molecules. And as we can see that they are both quantities are increased function as a function of number of molecules. The number of molecules is increased. We increase the number of molecules until we reach a value that gives the maximal allowed bonding energy. So in this talk, I give two different systems and two different mechanisms to illustrate the underlying mechanism of storage hydrogen in different systems, and the different strategies to improve the hydrogen properties. Okay, the next slide, please. Thank you for your attention.